Right. So thank you so much for inviting me and for giving this me this opportunity to talk about the work. Of course, if anybody has questions, I still have not figured out how to get the chat window up while I'm talking, but please feel free to interrupt, or if one of the moderators wants to interrupt for somebody who has a question in the chat, please feel free. It's always more fun to chat about the work than just a one-way presentation. So I'll begin by saying that this is, of course, work that I've done with a great collaboration of people. Don Wilcox is a postdoc at Lawrence Berkeley National Lab. Nicole Ford is an intern there, and Andrew Myers is another postdoc at Berkeley Lab. And they've been absolutely great to work with, and this would, of course, not be possible without them. So I'm going to start just by remarking that this planet that we live on is a very interesting condensation of a bunch of the very rare elements in the universe. And you can see this for instance, by looking at the sun as a representation of what the sort of typical abundances around us are outside of the Earth. And it's, of course, mostly hydrogen and helium with some trace amounts of other elements. And everything that we interact with here and everything that we are is some of that trace elements that was formed somehow since the beginning of the universe. And so, for instance, you can see here that like there's carbon, nitrogen, oxygen, all these the basic elements that we need for life are much less abundant than hydrogen and helium. But somehow these elements were not born in the early universe at these abundances, and somehow we had to create them. And so the natural question is, of course, where did these atoms come from? And as most people probably know, because Carl Sagan very much popularized this point, we are all made from star stuff. And so if you want to combine atoms into other atoms, you need to be able to smash them together. And in order to do that, you need to get a bunch of atoms in the same place. And that's exactly what stars are. They gravitationally just collect atoms in the same place and smash them together. And so there's that's what stars do in general, but you can't just have a star because the Earth can't form inside of a star. So somehow you have to get this matter out from the star, and there are a few ways of doing that. There's two general classes of supernovae, 1A supernovae and core-collapse supernovae. And so the idea is if you explode a star, you can extract all those heavier elements that you formed inside of the star. In the case of core-collapse supernovae, this is a large star its core becomes gravitationally unstable and collapses. And this collapse releases a bunch of energy neutrinos, which blows up the rest of the star. And so you get a bunch of this matter ejected. In 1A supernovae, it's a thermonuclear detonation of a degenerate core or a degenerate white dwarf that yields the explosion. In both cases, a bunch of the original matter in the star is ejected, but there's also a good amount of nucleosynthesis happening during the explosion as well. So in the case of core-collapse supernovae, the matter falls in and is, at least in the early stages of supernova, the shock is strong enough that it completely dissociates those atoms into free nucleons. And as this matter is ejected, those nucleons recombine into new elements. So there's a lot of nucleosynthesis both in the original stars and in the explosion itself that yield a bunch of these elements. But this can only explain elements up to about iron or so. And so there's a whole bunch of other elements that are much larger but can't be explained by ordinary supernovae. And so these elements require, turns out they require neutron capture. So the idea is if you have a seed element and you bombard it with neutrons, the seed element, one of these lighter elements will grow. You just add neutrons to the element. And if you add enough neutrons, it becomes unstable to decay, and it will it will convert some of those neutrons to protons until you get back to a stable element. So there's a natural timescale there. That's the timescale that this decay timescale. And so there's two general classes of how this capture works. Either you capture neutrons much more quickly than you can decay, or much more slowly. So in the case of the slow neutron capture process, you accumulate neutrons. So you accumulate one neutron at a time, and then you convert it to a proton. Then you accumulate another neutron, convert it to a proton, something like that, so that you always stay very close to a stable element. Whereas with the rapid neutron capture, you just pile on the neutrons faster than it can decay. And these produce different distributions of these final elements. And it turns out that it's actually both of these processes are needed to explain the abundance of all these heavier elements. So of course, the ones that we like to talk about for the rapid neutron capture process are gold and platinum, because everybody likes shiny things. And these are primarily produced by the R process. But then there's also, for instance, europium, which is another heavy element and is produced primarily by the R process, but also is the most easily observable of these elements. So it's often used as a tracer of this rapid capture process. So then, of course, if we want to bombard these lighter nuclei with neutrons, we need some situation where we have a bunch of neutrons at hand. And so in just thinking about all the things out there that have a lot of neutrons and yield explosions to eject a bunch of this matter, there's the natural answer is something dealing with neutron stars, because neutron stars are made primarily of neutrons. But there's also, for instance, in the final stages of lower mass stars, the stars can be unstable and mix up some of this slow R process, or sorry, that doesn't make sense. Some of these slow neutron capture process elements and eject them out from the star. But for the rapid neutron capture process, we need all these neutrons. And so there's two, if you have a lone neutron star, nothing's happening to the matter. The gravitational field is very strong. None of those neutrons are going to escape. So either you cause an explosion during the formation of this neutron star, and you extract some of that neutron-rich material from the explosion while it's happening, or you wait until you have two neutron stars or a neutron star and a black hole, smash them together, and the matter that's ejected is very neutron-rich. And so for a long time, it was actually core collapse supernovae that were thought to be the dominant site for this rapid neutron capture process. But now the popular idea is neutron star mergers, and for good reason. So neutron star mergers are also interesting, not just because of the elements that they produce, but because they're involved in a bunch of other mysteries as well. So there's, of course, been a huge fuss made over neutron stars in the last few years. So why is this? So there's a large number of transients that we can observe, and these span a wide range of transient duration and transient brightness. And as bigger and better telescopes are being built that observe deeper and wider fields of view and with higher cadences, we're able to see a bunch of these transients that we simply couldn't see before. And so that the signal from a neutron star merger is one of these. So that's this kilonova block over here, where it was previously just the right combination of dim and quick that it was very easy to miss. And so we, of course, want to, if we see things exploding in space, we want to know what happened. And kilonovae are the result of neutron star mergers are part of this puzzle. Of course, like I mentioned, we think that neutron star mergers are the origin of at least some of the heavy R process material in the universe. And this can be seen through a variety of sources, both through the evolution of elements in the universe. So this is the europium is a function of iron. And so there's this trend which shows that iron production and europium production are linked. But there's also just observations of the signal itself. So this is an example of theoretical light curves of a kilonova. And this is the classic example of if you have a lot of lanthanides, so a lot of these very heavy elements, then it's very optically, the ejecta is very optically deep, and you get this slower, dimmer light curve. So this is just brightness as a function of time. And if there isn't much of this matter, you get a very rapid rise, much brighter signal, but also a more rapid decay. Now, if you look at, for instance, the spectra of from this light, it's these are the same examples of the same simulations with different amounts of these heavy R process elements. And what you can see is that there are definite differences depending on what elements you produce, but it's not like there are discrete line features that you can extract the actual elements that are in that ejecta. It's very smeared out. These atoms that are produced are very complicated, so there's a huge number of lines. And so you can't actually read off what elements are in the ejecta. You can just say, I know that it's very optically deep, and I know there's a lot of these heavy elements, but you don't know which ones. So this is still a bit of an open question. Neutron star mergers are also linked to short gamma ray bursts, which has, of course, been a mystery for quite some time. The natural question being, we see these extremely bright bursts of radiation from across the universe. How can we get enough matter in enough energy in such a small area that you can yield such a short and bright burst? And neutron star mergers might be the answer. And of course, there's the trying to understand how massive black holes form. So we have a bunch of observations of stellar mass black holes, and we have a bunch of observations of supermassive black holes. And so one of the open questions in astrophysics is, how do you get from these stellar mass black holes to the larger black holes? And so one potential idea is that you combine these smaller black holes and make bigger ones. There are a bunch of rate problems with this, but this black hole formation is part of the story. So let me back up and try to go through the physics of what's actually happening inside of a neutron star merger. So when you have a neutron star, and black hole that are orbiting each other, the orbit will decay because of gravitational radiation until one or both of these neutron stars is tidally stripped. This will eject this neutron-rich matter that we want in all directions, and what will remain is a central compact object, either a permanently stable neutron star or a temporarily stable neutron star or a black hole that's surrounded by an accretion disk. This accretion disk is very, very hot, hot enough that it's going to be emitting a bunch of neutrinos. And these neutrinos are responsible for a number of things, one of which is deriving outflows from this disk. So the neutrinos, just by depositing energy in the sparser outer regions of this disk, can derive a significant amount of mass off of the disk. Neutrinos are also responsible for changing protons into neutrons. So if you're ejecting a bunch of very neutron-rich matter, but you're irradiating it with a bunch of neutrinos that cause it to that turn a bunch of those neutrons into protons, you no longer have this environment that's conducive to forming these heavy elements. And neutrinos can also, if one idea for how you can generate some of the energy for gamma ray bursts is if you have neutrinos streaming from opposite sides of the disk and annihilating in this polar region, you can deposit a large amount of energy that may be enough to drive these relativistic outflows. It's magnetohydrodynamic stress is more popular of an explanation for this, but the fact remains that there's still a lot of energy that's being, probably a lot of energy being deposited from neutrinos annihilating here. So the neutrinos are really a dominant piece of the picture of what's happening in neutron star mergers. We have, there's a lot of work going into understanding neutron star mergers. There's a lot of very sophisticated simulations that show this merger process. We have, as of a few years ago, a direct observation of a neutron star merger on several fronts, including across the electromagnetic spectrum and with gravitational waves. But then the question is, do we really understand this? There's a lot of questions that are still unanswered that can't be answered by the simulations and the observations that we have right now. So for instance, how is this outflow launched? Do we actually know that the outflow, that we're correctly understanding how this matter is ejected via the dynamical, the tidal shredding and with neutrino losses and MHD stresses from the disk? When you merge two neutron stars, does a black hole form? When does the black hole form? How long is this central neutron star stable? In this ejecta that we see, are we seeing a bunch of heavy elements that explain the origin of our process elements in the universe? Or is it some distribution of elements that doesn't match what we see, and so it can only be a partial explanation for the elements that we see? Does another way of stating this question is, do the abundances in the ejecta actually match the abundances that we see in the sun and that we predict from theoretical calculations? And then also, of course, are we seeing new physics? Neutron stars and black holes are prime laboratories for exploring new physics because they are some of the most extreme environments in the universe. And so if there's somewhere that we're gonna see something new, it's gonna be a neutron star, something like neutron star mergers. And so we want to have a detailed understanding of everything that's going on, so that we know that if we can say that if the simulations don't match with what we see, we can argue that this implies that there's some aspect of new physics that we need to explore to actually understand what's going on.
Hey, Sherwood?
Yeah.
There seems to be something blocking the central part of your title. Probably the Zoom participant list or something. Is that movable for you?
Let's see, does that help?
I may yeah, that helps. Thank you.
Okay, thanks for pointing that out. I will try to keep that moved out of the way. Okay. So then, as a computational physicist, what I want to do is, if there's a problem I don't understand, I want to model it to show numerically because we can't solve these equations analytically. We want to solve them numerically to see if what we're observing is consistent with the theories that we propose that explain them. So there are a variety of different aspects that go into this modeling. We need to account for general relativistic magnetohydrodynamics. We need to account for a nuclear equation of state, because the matter in these neutron star mergers is at or above nuclear saturation densities. And we need to account for radiation transport. In the case of the merger dynamics itself, we need to account for neutrino radiation, as neutrino carries energy and lepton number around the system, and also at later times, once the to model the electromagnetic signal that we get, we need to simulate electromagnetic radiation. So let's talk about what this looks like in more detail. So for instance, if we take a piece of this merger, so let me explain what these images mean real quick. So this top left plot, all these plots are slices of a neutron star merger simulation. At the center is this black hole, and on the outside is an accretion disk that's orbiting around this black hole. So this plot here is a color plot of the density. So this is the dense part of the disk. This is the electron fraction. So you see the disk is very neutron rich, whereas these areas above the disk are much more proton rich. And so we want to understand the electron fraction of the matter that's ejected from above the disk. This is the temperature, showing that the temperature in the central parts of the disk is several MeV. This is plenty hot enough to produce a large number of neutrinos. And the velocities are also very large. So this is the velocity as a function of, as a fraction of the speed of light. And in the equatorial regions, this is the orbital velocity is a significant fraction of the speed of light. And in the polar regions, the matter is being ejected radially outward. So there's high equatorial speeds and high ejecta speeds. If we, this data is from Radice's 2018 simulations. These are 3D simulations, but these are not the 3D simulations that I'm talking about. So if we, I'll explain more later. So if we take a piece of the simulation, say just a small cube, like a 1 centimeter cube inside of this domain, this cube is going to be filled with a bunch of different things. There's going to be a bunch of protons, neutrons, electrons, neutrinos, force carriers, magnetic field. But the way this is modeled is if we take this cube, we model we say that there's some inside of this small representative cube, there's some matter density, some temperature, some electron fraction, the velocity of the fluid, the magnetic field, the general relativistic metric, and also some quantity representing a density of neutrinos. And the idea is that you fill this domain with a bunch of these cubes, and you compute the fluxes between each cube, and you take a small time step. And so for instance, if you started with a bunch of matter in one cube, this matter would flow into other cubes. And so you calculate this flux, you take a small time step and say how much matter moved from each cube to each cube, and you update the values, and you keep marching along forward in time. And you take this data and make plots like the ones here. This is these are robust solutions to the equations, and that if you make these blocks smaller and you take smaller time steps, these formally converge to the actual differential equations that we're solving that describe the evolution of all these variables. But in practice, these equations aren't solved exactly. Most of them are solved with some level of approximation. Oftentimes, that is not a convergence approximation that will converge to the correct answer with increasing resources. Many of these, for instance, the treatment of how neutrinos move around in these simulations are done very approximately because they are incredibly expensive to treat. So this is an example on the right side is a analysis of the difference between a Monte Carlo direct evaluation of what the radiation field should look like and a two-moment representation. So there are a few different methods of treating radiation transport, one of which is Monte Carlo, which is known as an exact method, and that it treats both the transport equation exactly. And the moment method is a lot cheaper, a lot more a lot faster to simulate, but it comes with its own underlying assumptions. And so it's this is a known problem, and it's been discussed a lot in the context of supernovae, but the problem is especially bad in neutron star mergers. So this is these plots are an analysis of the error in the assumptions made by using this more approximate method. And especially in these regions, these boundaries of the disks, which is where all this mass ejection is happening, there are large differences between the formal Boltzmann solution and that assumed by the moment equations. And this isn't just an academic exercise. If you look at the difference between, this is a paper from Radice in 2018, looking at different treatments of neutrino transport in these merger simulations, and you look at the elements that end up being formed from these simulations, the computational treatment of neutrinos yields big differences in the elements that are formed in the ejecta. So these dots are the solar abundance of these elements of each mass, and the different colored lines are the results of simulations with different treatments of neutrino transport. And so we want to treat the neutrino transport as accurately as possible so that we get so that the abundances of the elements we get from the simulations are actually representative of what the equations would predict. So let's take a step further. So I've been harping on the fact that neutrino transport is very important to treat accurately. Another aspect of neutrino physics that we need to consider is the fact that neutrinos of different flavors do different things. So for instance, if you have a electron neutrino and a muon neutrino, the electron neutrino will be able to convert neutrons and protons between each other, but the muon neutrino won't. And this just comes down to the fact that the energies are high enough to produce electrons, but not muons. And so this results in some difference between the abundances and the reaction rates for electron neutrinos and muon neutrinos. So if we look at an individual neutrino, for instance, this neutrino is described by a quantum wave function. And in this case, this green curve represents the wave function for electron neutrinos. And the blue line here is the wave function for muon neutrinos. And because this neutrino is born as an electron neutrino, all of the amplitude is in this wave packet for electron neutrinos, and none of it's in the muon neutrino wave packet. But it turns out that neutrinos actually, you can't represent them just as one flavor or another. They're really a quantum superposition between these states. And the quantum basis that says that, you know, either muon, electron muon or tauon neutrino, this is a 3-element basis. It's not the only basis that you can use. And so there's another basis, the mass basis. So if you take this neutrino wave function and you break it down into the mass basis, this actually has, this electron neutrino has a combination from, it is a quantum superposition of neutrino states that have different masses. So this neutrino does not have a definite mass. So this shows this is an example wave function of a neutrino with 2 different masses, one mass described by the red curve and one mass described by the yellow curve. Now, as this neutrino is moving, because the 2 different wave functions, the neutrinos described by the 2 different masses will have different speeds, these wave functions will move forward at different speeds. And so, for instance, at a small time later, the wave functions might look like this, where the yellow wave function has just moved forward a little bit faster than the red one. And so these peaks no longer line up. So if you do this basis transformation back into the flavor basis, you get something that looks like this, where there's now a quantum superposition, like both the electron wave function and the muon wave function are have large amplitudes. So just by the fact that different masses of neutrino move at different speeds, these wave functions shift, and you transform flavor. So after this time step, it's not just an electron neutrino. Now it's a quantum superposition between an electron and muon neutrino. Now the mass is not the only thing that changes speed. Just like if you roll a ball up a hill, and you give it some momentum to go up the hill, the speed will be determined both by the mass of the ball, but also by the potential, the height of the hill. And so if different flavors experience different potentials, they're going to move at different speeds, and this will change how the flavor transformation happens. So let me talk about something a little bit more familiar, just as an aside for comparison. You can look at, for instance, electrons in a plasma. If you, so this particular simulation is a two-beam simulation of the two-stream instability. So this is a domain, as a function of position. There's a bunch of electrons, both moving in the forward direction, and also a bunch of electrons moving in the backward direction. And these electrons feel each electron feels the impact of all of the electrons around it. This turns out to be unstable. So as you let time progress, the momentum of these electrons will change. So because there's some initial perturbation in the electron positions and velocities, this is going to influence the electromagnetic fields, which in turn are going to influence each individual electron. And it does so. This feedback loop proceeds in a way that causes the momentum of these electrons to change very rapidly. So you get this instability that results in this this mixing of the original electron momenta. And this nonlinear behavior is a result of the fact that the electron momentum or the electron velocity influences the electromagnetic fields, and the electromagnetic fields influence the electron velocity, and there's a positive feedback loop. It turns out the exact same thing happens for neutrinos, but instead of neutrinos feeling an electromagnetic field, they feel the flavor distribution of all the neutrinos around them, of all the neutrinos and all of the other mass around them. So if there's an initial perturbation in the flavor structure, this flavor structure will change what other neutrinos feel, which will change how their flavor changes, which in turn will change how each neutrinos changing flavor changes how neutrinos change flavor. So it's the same positive feedback loop. And so you can set up situations. This is another simulation where we have two neutrino beams shooting at each other, but rather than the momentum of the neutrinos getting mixed up, it's the flavor of the neutrinos that get mixed up. And so this is an initial distribution that's entirely electron flavor neutrinos, and the amount of muon and tau neutrinos is 0. And as time progresses, this instability grows and quickly saturates, and you end up with a mixture, in this case, a nearly even mixture of all of the 3 different types of neutrinos. So the natural question is, this aspect of the physics is something that hasn't been included in the simulation so far, because this instability happens on an extremely small time scale and length scale. That is something like picoseconds and sub-centimeter length scales. And this is something that you simply cannot evolve directly in these simulations. But what we want to do is understand, if we have this instability, we want to know how much of each flavor neutrino is present after the instability mixes everything up. That's the big question that we want to know. So the work so far that's been done, people have done linear dispersion analysis, saying if I have some neutrino distribution, what modes grow? How quickly does this instability grow? And so one of the predominant outcomes from this analysis is that if you have, so this is an image of different neutrino distributions at a particular point. The electron neutrino distribution in this picture is very isotropic. There's just as many neutrinos moving in all directions, whereas the electron antineutrino distribution is much more forward peaked. So there's more antineutrinos than neutrinos moving in the z direction, and more neutrinos moving in the minus z direction. And so there's some point where these distributions cross. That is to say that there's just as many neutrinos as antineutrinos moving in this direction. And one of the predominant outcomes of this theoretical analysis is that if you get this situation where there's a crossing in the distribution, we expect it to be unstable. What this doesn't say is how much the flavor ends up changing, how much ends up getting mixed up. It just says that it's unstable. And so one of the things that people have been doing is looking through these regular simulations that don't include flavor transformation and trying to hunt down the situation where there's these crossings. And also there have been a series of approximate one-dimensional simulations that each of these simulations has their own choice of symmetries that they impose. And so they're a bit hard to piece together because they all have various symmetries. So my goal, this font got very messed up. Sorry about that. my goal is to determine the neutrino flavor abundances after the fast flavor instability saturates. So the way we do this is with a new code that we wrote, just do this. So this is based on, because this looks a lot like the plasma physics having to do with electrons, we imported some of the technology of plasma physics, that is particle and cell codes, to do the same thing but with flavor, neutrino flavor, rather than electron movement. So this code emu, a particle and cell method, arbitrary flows and on Cs and GPUs. So this particle cell method, the way it works is we have some a computational particle that represents a large number of neutrinos, and we assume this particle has some cloud, some spatial distribution where these neutrinos sit on the grid. And so this particle itself will move on the grid. The particle will contribute to the background field, and so in each time step, the particle will deposit some of its flavor into the background field on the grid. It will move some amount and change flavor according to the potential that it reads from this grid, and then it will change flavor. So this particle will actually physically move in space and change flavor as it moves. So yeah, we initialize the particles, we deposit the potential on the grid, we move them and evolve the flavor, and keep doing that over and over until the end of the simulation. And so each particle itself, the way we represent the quantum state is with a 3x3 matrix, where the diagonal elements represent the amount of each of the flavor eigenstates, and the off-diagonal elements represent the quantum mixing. This density matrix approach is a full description of the quantum state of each individual neutrino contained in that particle. And then we just simulate a large number of particles. So the first thing that we want to do is show that this works in, this matches theory. So there's a theoretical, there's a test problem that has a known analytic solution. This is the two-beam model. So if you shoot electron neutrinos in one direction and electron antineutrinos in the other direction, you expect that this flavor instability to pick up at a known rate that you can calculate. And so that's what this is showing. This rho E mu is the density matrix for the quantum mixing between the electron and muon states. And this grows exponentially. So this is time and the size of this off-diagonal element. It grows exponentially, and the rate of this growth matches exactly with what theory predicts. So this consistency check, it works great. So now what we want to do is do the same thing for something that doesn't have such an easily answered as an easy analytic solution. So in this case, rather than having two beams, we have two broad distributions moving past each other, where electron neutrinos are moving to the right and antineutrinos are moving to the left. That's what this distribution shows. It just says there's a lot of neutrinos moving to the right and not many moving to the left. And this is a video that I showed before, where you start off with entirely electron flavor neutrinos, but very quickly it grows and the instability grows, and you mix up all these flavors completely. So this, if we don't want to look at that very quick movie, this is just some snapshots from the movie. So these are the initial conditions. There's a linear growth phase where this the flavors of these. So this is the position and the amount of each flavor is on the y-axis. And so there's some fluctuation throughout the domain, and this fluctuation grows exponentially with time. That's the linear growth phase. And then at some point, it can't grow anymore, and so it saturates, and you end up with a random chaotic distribution of neutrino flavors. And this, at least in this one simulation, it tends toward having even numbers of all flavors of neutrinos. So this is very useful information. If all of the flavor instabilities behaved like this, where we know that if it's unstable to the fast flavor instability, then we know that we're going to end up with even numbers of all three flavors. We can just put that into simulations and run the simulations and get some estimate of the elements that form. The problem is that it's not necessarily that easy, and so we want to simulate a large number of these to make sure that we actually understand it.
Sorry to interrupt you. Can I ask you
Yeah,
what
sure.
you mean? What do you mean by even numbers? You mean that 1/3, 1/3, 1/3, or something different?
Yes, exactly. So since there are 3 neutrino flavors in this simulation, so there's even numbers. The blue, the red, and the yellow are all at approximately 1/3 of the total amount of neutrinos. Yep.
Okay, cool. Thank you.
Thanks. And any other questions? All right. So one of the neat things about this project was we implemented this physics and into the code, and the code was actually teaching us about the neutrino physics, all the stuff that a bunch of the theorists already knew, but I didn't already. And so we saw this interesting behavior. So this is the quantum mixing is represented with an imaginary number, which has a complex, or a complex number which has a complex phase. This is just in the real imaginary plane, what's the angle of for the number, what's the angle of the complex number in the real imaginary plane. And so there's this structure that moving forward in Z, this off-diagonal element has this very regular structure, so that the phase just increases with Z. And so this is a regular wave structure, and you can read off the wavelength of this wave just by the distance between where the distance between points of the same phase. And this wavelength matches exactly with the wavelength of the fastest growing mode. So this is exactly what you would expect. In addition, if you look at the flux rather than the number density, the same quantity for the neutrino flux has a much larger wavelength. And it turns out there's not only one unstable mode, there's an entirely separate branch that has a different fastest growing mode, and this wavelength matches that exactly. And so these simulations were teaching us that there's not just one mode that grows in these unstable situations. There's a large number of modes that are superimposed. And so we learned, we derived this dispersion relation after the fact and found that it matches exactly. You can do the same thing with the growth rates. So this dispersion relation says that for a given wavelength, how quickly does the mode grow? And so you can read that off of this plot here. So this is for this, the mode represented that you can see in the number densities, it grows at the rate we predict. And the mode seen in the fluxes, it also grows at approximately the rate that we predict. It's a little bit off, and we show in the appendices that this is a matter of numerical fidelity. So as you increase the number of grid zones, you converge on this growth rate. So the growth rates match. So now some of the things that we learned. First of all, you look at this the growth rate of the second mode. This is a anisotropic mode. And although you can see that this faster growing mode saturates at about 0.27 nanoseconds. But when that saturates, it also seems to kill the growth of this slower mode. And so this is a very interesting result. Even if you see an instability, it doesn't necessarily mean that it manifests in the large scale flavor structure. It might just be the case that once the fastest growing mode saturates, all bets are off and you no longer get this coherent linear growth. So this is a mole-wide projection of neutrino flavor, just picking a single point in the domain. You can look at neutrinos moving in each different direction, and you can ask what the quantum state is for that neutrino. Each of these dots is a single neutrino in that computational grid zone. And where this neutrino, where the point is located, is the direction that's moving. So these neutrinos are moving in the x direction. These neutrinos are moving in the -x direction, etc. And the color shows the quantum state. And the biggest thing that you pull out of this is the fact that there's a lot of symmetry around the equatorial direction. So even though this is deep into the random state after this instability saturates, even though there's a lot of random stuff going on, you still maintain this high degree of azimuthal symmetry. And that's a function of the fact that the fastest growing mode is azimuthally symmetric. So yeah, you don't necessarily expect this to mix up everything in all dimensions. There are some things that stay very regular. So we can also look at the Fourier space for this. So this is the same quantity. This is the same electron muon off diagonal component, and this is the Fourier transform where each of these lines is a different point in time. So this the yellow curve, or sorry, the salmon point here is just before the instability saturates. And so you see that there's this some wavelength that grows much faster than the other wavelengths. And just the wavelength that grows fastest is the fastest growing mode, like we expect. But then the instability saturates, and you end up in this situation where there's these tails that go out. So this is a log linear plot. So these are exponential tails. And I've also, let me move this out of the way. If I scale this x-axis by something like the square root of time, these all line up with each other. So this is a diffusive process in momentum space. So after the instability saturates, there's diffusion going on that spreads the power out from the wavelength of the fastest growing mode to increasingly higher and higher smaller and smaller wavelengths, higher and higher wave numbers. And so it will spread out and become much more mixed in momentum space. The last thing to point out is that we did these simulations for a large, not a large, some initial small number of parameters. So rather than having even numbers of neutrinos and antineutrinos, this is an example of decreasing the number of antineutrinos. And so as you go from this light yellow curve, this is the case where there's even numbers of neutrinos and antineutrinos. And that shows, so the instability starts at very quickly. You see a large amount of flavor transformation. And then at later times, you settle down to this state where the number of electron neutrinos is approximately 1/3 of the total neutrino distribution. Now, if we decrease the number of antineutrinos, this begins to change. So in the limit of 0 antineutrinos, the distribution is not unstable and nothing changes. So you don't mix up any of the flavors. And in between, as you decrease the number of antineutrinos, you decrease the net amount of final mixing. So what this says is that the details of the neutrino distribution in each cube in your neutron star merger that you look at, that will determine both how quickly the instability grows and also how much neutrino flavor is mixed in the final state. So it's not true in general that if you are unstable to this fast flavor instability, that you will evenly mix all the flavors. There's dependence on the details of the distribution. And this is important. So all the analysis of neutron star mergers so far does, because it's hard to simulate this, the first approach is to say, well, what if all the flavor is evenly mixed wherever there's instability? And that's what these works have done. For instance, this is from a paper from George in 2020, where you look at the distribution of elements with neutrino oscillations and without neutrino oscillations, where with neutrino oscillations just means you assume that everything is perfectly mixed. And you get very different distributions of the abundances. But so what this says is that if in general we expect that the amount of flavor transformation to be less than this, we should expect that the effects on the nucleosynthesis should be smaller than what are predicted by these analyses that include oscillations via some approximation. So now the promised three-dimensional simulation. So this is the snapshot in, or a movie in 3 dimensions, where I'll play this a couple of times. The diagonal elements, so this is the same snapshot for all these different elements. This diagonal element represents the number of electron neutrinos. This is the number of muon neutrinos and the number of tauon neutrinos. It starts off in a distribution that's entirely electron neutrinos, and And so you get more and more muon and tau neutrinos as a function of time, just like with the one-dimensional case. Same thing is true for the off-diagonal elements, which represent the quantum mixing between the flavor states, and they get mixed up as well. And this shows that as you go later in time, let me go back here. Okay. So as we let the simulation progress, so this is the linear growth phase that I mentioned before. You can see this regular pattern in the phase of the off-diagonal component as a function of z. And so this is the same thing that we identified, the wavelength, that is the distance between these white points going in z, is the fastest growing mode. By simulating this in 3 dimensions, you see that there's extra structure in the other dimensions. But in general, the growth rate and the wavelength of the growing modes and all that stuff is largely the same. And at late times, once this all decoheres, you get the same distribution, an even distribution of electron, muon, and tau neutrinos. So in that regards, this 3D simulation behaves exactly like the 1D simulation. The only differences that we see are this structure in other directions in the z direction, which you obviously wouldn't get with a 1D simulation. And the only difference that we see is that the rate at which you decohere to this even flavor mixture is faster in 3D than in 1D. So this decoherence process is different, but otherwise it can be very intuitively understood by the 1D simulations. Okay, so that concludes everything. So I think that the thing I want you all to take away from this talk is that neutrino flavor transformation definitely does affect the elements that come out of neutron star mergers. And we now have methods to simulate this in 3 dimensions so that there aren't artificial imposed symmetries. And so what we need to do now is do a bunch of these simulations so that we can actually develop an effective model of what distributions lead to what mixture of neutrino flavors. So we have a few clues. We know that for the simulation that we simulated, it goes to even flavor mixtures, but this is not true in general. We can simulate things in 1 dimension, and at least for the case that we simulated, it behaves very similar to the 3-dimensional simulations. Yeah, so what we want to do in the future is apply this to a much larger number of neutrino distributions to sample what the neutrinos look like inside of an actual neutron star merger and begin to really understand in a predictable way what abundances of neutrino flavor occur in supernovae in neutron star mergers, so that we can feed this into simulations and get realistic numbers for the abundances of various atoms that form from the ejecta. And with that, I'm happy to answer any questions. Thanks so much.
Thank you for the very interesting talk. Yeah, any questions? Yeah, Sean, you're unmuting yourself, right?
Oh, no, I didn't have a question. Sorry.
Okay, sorry.
So I will also point out that this is developed entirely in open source. So it's downloadable and modifiable. So yeah, it's completely open.
Yeah. Mike, you've raised your hand.
Hey, Sherwood, thanks for the talk. I had a question about EMU.
Mm-hmm.
Does it have so I'm kind of looking forward to like exascale era, where now we're going to have these much, more powerful machines. Does EMU have enough components that are parallelizable where you'll be able to take advantage of these bigger machines?
Yeah, so it's built on the AMREX framework. So that doesn't mean automatic scalability. We do still have scalability issues, but yes, right now we're running, it's most efficient when we run on GPUs. It parallelizes very well with GPUs. But yeah, so Dawn has run this, I think, doing some scaling tests up to a few thousand GPUs. And I think we only get good scaling up to maybe 100 GPUs or so. But yeah, we're still trying to push forward the optimization. But yes, it's designed from the ground up to be scalable.
So I have a question. Hey, Sherwood. I think I'll talk with you right after this. So I wasn't officially on your schedule until the middle of your talk. So
Sure.
So are there prospects for how you might, so I mean, because these are relatively small scale simulations, they're telling you about, okay, locally what the neutrino field is doing. Have you thought about how you might be able to include this in moment-based methods with some sort of source term between different flavors or that kind of stuff?
Yes, I've thought a lot about how to do it in a moment treatment. And so there are some, so for instance, there's a one work done by CJ Stapleford where they essentially take, it's not a moment-based description, it's a discrete ordnance description, but the same concept applies, where they evaluate some flux between different flavors. I think in our case, we don't necessarily want to do that because the fluxes are going to be much, much larger and much faster than any of the things that we're simulating on the large scale. And so really what we need is an effective treatment where we can just recognize the fact that it is unstable, and then between time steps, just shuffle the flavor around and to the appropriate distribution. So I think that's what's going to end up needing to be done. But that hasn't been done yet.
Okay, interesting. Thank you.
Any more questions? If not, then I'd like to thank you all for coming. Thanks again for the very nice, very interesting talk. And I hope to see you in 2 weeks. Thanks, everyone.
Thank you very much for the nice talk. Bye, Sherwood.